So we were talking about the wave particle duality of light. So our author has actually chosen to look at diffraction of light through apertures and a few things that are there. And so if we have a circular aperture, we're going to get these kinds of fringes. And I was pointing that out to you that if we did that with X-rays, we can start looking at atomic structure. And you'll start to getting how these waves can be additive or subtractive. There is one going out, there's a reel going around right now, whether you're on TikTok or Facebook or whatever one you want. They actually had a beautiful set of waves that the Atlantic waves were coming in onto shore, and there was a wave coming off of the shore, off of the, I believe it was in Sweden. And you had these lovely straight lines of two water waves coming together and moving through each other. And you could actually see the waves become additive, and then you could see the waves separate. And it was a really nice way to look at waves and how those are going. When we're starting to deal with light, our shapes are going to come into play. And we will get a variety of different things happening. So we've talked about reflection and refraction, but thin films are going to cause these various colorations as well. And basically what's happening is we're taking the waves, are getting constructive or destructive interference, and we're going to start seeing those colors. So if you've ever looked at oil on water, or after the rainstorm and you get that greasy layer that's on there associated with the oil that comes out on the roads, this is going to be more of that situation. You're going to get these things that are directly out of phase with each other, and you're going to get those pieces. To get this kind of an image, you can use that with layers of soap bubbles. So if you're playing with soap bubbles and you're looking at those soap bubbles, you're going to get these colored layers from thin films in a variety of different places. We use thin films in a lot of places. On our eyeglasses, we use them. You get thin films on the inside of layers in your car. And depending on what angle you're looking at it, you're going to get these kinds of interference patterns. We use diffraction gratings. Diffraction gratings are going to work like a prism. So if we did a traditional prism, we get that spread out of the light. Well, a diffraction grating is going to be able to spread that light out as well. And depending on what's causing our plasma or our light, so if you were to look at yellow street lamps at night, those yellowish colored ones, those are sodium lamps, and you'll get nice bright yellow lines with a diffraction grating. If you look at the bluish green ones, those are mercury lamps. If you look at our mercury vapor traditional fluorescent tubes, you're going to get mercury lines, and you'll see those blue lines in our diffraction gratings. LEDs aren't going to do that as well because they're not generated by the excited gases. Neon, which is why we've got a lot of our laser pointers or helium neon lasers, they're going to give us some nice red lines. Our neon lights will give us nice red lines, but sodium gives us these nice yellow lines. Helium, we first detected helium on the sun by doing something associated with our diffraction gratings. So we have those. We can utilize a lot of different instruments. This is a Michelson and Morley interference. So we can set it up to get our things in and out of phase from each other so that you can get the rings. We use these interferences to detect slight effects. We use interferometers, and it doesn't matter the waves, even though the waves we started with these detectors and these interferometers we're utilizing for light, that's it's the interferometers out in Louisiana and in Washington that actually measured gravity waves. And there's papers outside of outside of this room on this campus that shows the interferometers that they've got. And the legs of the interferometers for gravity waves are at least a mile long. So in order to get that slight detection of that interference for gravity waves. So that kind of is our summary, but I wanted to kind of bring through, she's actually done the mathematics for you. We are really only going to focus on doing the Snell's law, but you can start seeing the limits that you can start to get through. And this is why I said we'll start to be able to tell shapes. Because if I get a square aperture, I'm going to get these types of diffraction patterns so that you'll be able to see those. Here's another good picture of my simple foot slope films. And again, what we're doing is we're coming in and we're using a thin layer to get our things out of phase. And we get the, we are transmitted in phase and out of phase, just like with our other waves. So you've got these slides in here and that. Anti-reflective coatings, you have to actually tip them over in order to see them. And if you've ever looked at your glasses with anti-reflective coatings, you've got, you can actually see those. The differential are slits. What you're going from is a single slit to a double slit to multi slits. And those spaces are going to be able to break us apart. And there's your compact fluorescence with our nice, good mercury lines that you'll get into those nice mercury lines. And you'll be able to separate them out. They've got the helium neon or hydrogen lines. This shows you the path differences. Now remember, with a double slit experiment, we're only worried about these two, but that gives us our path difference. And you could also do this with Fresnel's lenses as well. And that's also going to give you your orders. So these give you your 0th order, your 1st order, your 2nd order. And you see that these aren't uniformly stretched out. And that comes from our dealing with our distances. And it comes from the fact that we've got a sine of an angle in here. And that's our integer that gives us that number. So you have those. And so we can do those. So like I said, I just was getting this so that you guys could get the images. But now you can see that how that if I'm using X-rays instead of visible light, I can actually look at doing the same things with my atoms in the structure. So we get those reflected pieces. And I think that's about where I'm wanting to. You can use, if you want to make a diffraction grating, old CDs. Old CDs will give you good diffraction gratings. You can go out in the YouTube and find out how to make diffraction gratings and reflections with old CDs all the time. And that spacing gives us the pits on the discs that allows us to do data layers and read data layers. And then we did our Michelson interferometer. Okay, so this sheet is introducing here the fact that while light travels through a vacuum, you are going to get a slight change based upon the medium that you go through. And that's what's going to ultimately give us Snell's law. So let's go there. There we go. And this was the presentation that I was using last week. All right, so we're going to start there. Okay. So we're for reflection and refraction. Reflection is the part of the wave that's going to bounce off the median. And it's going to work just like if we're doing a tennis ball, if we're doing a racquetball, if we're doing a golf ball. And if we hit it at an angle, we get that angle of reflection with that normal, what I showed you guys on Friday. We have our normal that's perpendicular to the surface, and I've got that angle coming in, and my angle of reflection is going to be the same as my angle of incidence. Now, my angle of refraction is going to occur when it goes into the medium. So what we discussed on Friday or last Wednesday, or probably both, is I'm going to get a bend towards the normal, or I'm going to get a bend away from the normal, depending on the ratios of my refractive indexes. So if I'm going from air to glass, it's going to bend inward. It's going to bend towards the normal. If I go from air to water, it's going to bend towards the normal. If I'm going from water to air, it's going to bend away from the normal. And we even showed that I'm going to ultimately get to a critical angle where I'm going to get a glassy surface. That's what I'm going to end up with. And you can have both processes happen at the same time. I can get a reflection and I can get a refraction. But what's going to happen is the intensity of the various beams are going to change. Luckily for us, in our physics class right now, we're not going to worry about that intensity. We're just wanting to know where the beams are going to go and how the beams are going to shift. We do want to know about intensity if we get to critical angles, but right now we're not going to play with that intensity so much. So we're going to use what's known as ray optics. We're going to simulate that wave front as a ray, as an arrow. We're going to make it look like a vector, okay? And we're going to say that light travels along that arrow in a straight line path. So we're going to be able to use those straight lines to allow us to determine where my angle is going to bounce off, where it's going to go. We're going to use that to determine how I'm going to form images with lenses and how I'm going to form images with mirrors. And we're going to keep that ray approximation. So the ray of light is an imaginary line that's drawn in the direction of our beam. But essentially, this is what it's simulating. It's a ray that's perpendicular to the wave front. That's what it's simulating. That's how we're going to be looking at it. So we're going to use that incident ray and that refracted ray and that reflected ray. So here is reflection. So as long as I have a smooth surface, I'm going to get it to come in and bounce right back off. And you can do it with a laser pointer. I can do it with a mirror. I can do it with glass, and I can be in there. And we are going to assume it's specular. That's going to give me my nice uniform surface, because we're going to see diffuse as well, but we're not going to play with diffuse. And if you've been driving up and down 60 lately, you see those piles of those different, it looks like little pieces of glass, it looks like sugar. That's what's going to give us our diffuse reflection that allows us to see our white lines and our yellow lines on our traffic lanes. But what that does is I don't have a nice smooth surface anymore, and my reflected rays are going to bounce off all over the place, and that's what's going to produce this glow. You're going to get this glow. Oops, that glow right there. You're going to get that glow because the surface is no longer even. It's not specular, and I'm bouncing it all around. Now, if I were dealing with sound, that's how you soundproof a room. Because we want to have all of those waves bouncing off so that we can maximize the destructive interference. So that's one of the things that we're going to do. But this is going to allow us to be able to see the road at night and be able to do a few things. But but we're going to go back here. We're gonna make the assumption for what we're gonna do over these next few chapters, that we're gonna get specular reflection, not diffuse reflection. So here's our law of reflection. It's very straightforward. We're gonna have our normal incident ray. So here's my incident ray coming in, and there it's bouncing out, and I'm gonna have those are equal to each other. So we're gonna switch. I'm gonna change my share here. Okay, that's interesting. Oh, that's off the physics text. It's going, why are we getting an Artemis rocket? That's why we're getting an Artemis rocket. Okay, so think of some devices here. Inside each of those is a mirror. Okay. And we're going to set this distance to be, we're going to make this 0.2 meters. All right. We're going to come in with a ray. We're going to make this side 0.5 meters. This is going to be 30 degrees. We want to know how many times this is going to bounce before it comes out. Okay. We want to know how many times it's going to bounce before it comes out. So if I've got it set up that this is right in line with that end. So the law of reflection is going to say this is 30 degrees. So now I have a triangle that this side is 0.2. We know that that angle is 30 degrees. And we could figure out that side. Right? Because what is it? It's the sine of the angle. Well, actually, we've got tangent of my angle is going to be the y over the x. X is what I want. Or no, this is x and this is y. So x tangent is going to be my 0.2 tangent of 30 degrees. This says that this part right here is going to be 0.2 or no, 0.115 meters. But now we can do this one because we know that this angle is 30 degrees. I don't have to do this calculation again because this will be 0.115. This will be 0.115. And then we get our angle again. At 0.115, 0.115. I don't know if it's gonna hit, but we're gonna do that. We got 0.5. It says I'm gonna get 4.3 of those. So this one would actually miss this if that were actually 0.5, because there's my 0.115, 115, 115, 115, and I get to a 0.3. So this one would actually move out if I have my 0.115. So I'm going to end up with one reflection, two reflections, three reflections before it pops out. So this just becomes a strict geometry problem. Or a trigonometry problem, because I got to figure out that distance, and trigonometry is the one that allows me to figure out that distance. But this would be a periscope. I'm doing a periscope. That's exactly what it's going to come up. And I can do it from a tank. I can do it from a submarine. I can do it from a variety of things, but that's essentially what they're doing. Usually what they're doing is the other way. A periscope actually is usually this way, that you have some reflective surface so that the person is looking at it from here. There's the eyeball, and it's collecting a wave in through here, and then it's funneling it down the channel. So it gets down the channel to ultimately get to the eye. So don't let these problems overcomplicate, because these are basically just geometry problems. Because you'll probably have problems that look like this. I've got a ray coming in, and I want to know if it's going to bounce and where it comes back out, how I'm going to redirect our ray. But that's basically all we're doing is, yep, if I've got this and then I have my normal, and we say that this is 45 degrees, and we say that this angle is 60 degrees. So this would become my 90 degrees. So this is going to be a whole angle of 150 degrees. We want to know how the light's going to bounce around. You might want to do it with a protractor, because you can do it by drawing just as easily as you can do it by calculation. So that's why we look at our reflection. Hey, Seth, what are you seeing on your screen?
I see your screen share.
Okay,
So
great.
of reflection.
Thanks. Appreciate it. All right. I'm still recording. Everything's seeming to work, so that's all good. There we go. Now I can see what I'm doing. All right, so that just gives us our angle of incidence. Now, when we go into refraction, we're going to get that bend. And the index of refraction, and we can use the index of refraction to determine what the material is. We can use the index of refraction to calculate that bend, and we can do it into each part of the medium. So this one is, we come in, we can still get a reflected ray, and then we can get a refracted ray. So this shows you all the various things we can get. So we've got, this is called smoke glass, so that we're actually seeing the ray inside the glass. So one is going to be our incident ray. And if we can imagine our normal here, we can see our reflected ray. Then my normal goes through and we can see the bend because this is lucite and it's got a higher index of refraction than air. It's going to bend towards the normal. And then it's going to hit the mirrored surface at the bottom, be completely reflected. And now when we come back out and I look at this normal, you see that it's bent away from the normal because lucite has a higher index refraction than air. So you can see all of those bends coming through. So we can do this and we know that it's reversible. We've got our ratio of the sines of the angles give us a constant, and that we talked about our bend towards the normal and our bend away from the normal. And because we are going through a medium, we're going to get a slight difference in the speed. And that's what our author was getting to with the idea of the swimmers. You know, if the swimmer is swimming in water, it's going to be one thing, but if the swimmer is swimming in molasses, it's going to be something else. So we will get it, and we do get that index of refraction. And the index of refraction is the speed of light in a vacuum divided by the speed of light in the medium. And for air and vacuum, it's very, very close to 1. It's slightly off in like the 5th or 6th significant figure, but it's very close to 1. So vacuum is 1. All other mediums are greater than 1. N is a unitless ratio. And as the value of light increases, or the value of N increases, the speed of light or the speed of the wave decreases. Now, it gets a little funky because then you have changes in frequency-ish, you know. As light travels from one medium to another, its frequency does not change. But remember, the speed is equal to the wavelength times the frequency. So we get some of there. So wave fronts don't pile up. They can be neither created nor destroyed. So that's going to give us that our idea that we don't get a change, and we just get our changes here. And the good news is we don't have to remember this anymore. Once we get into Snell's law, we don't have to worry about that frequency issue, which is great, which is absolutely wonderful. So you just remember Snell's law. So you have lots of indexes of refraction. There are tables of them. The Handbook of Chemistry and Physics has a bunch of them. Different types of glasses will have different indexes of refraction. Crown glass is usually the same type of glass that they used to make glass eyeglasses out of. Our polystyrene is 1.49, diamond is 2. So you can start to see those. This is also one way to distinguish clear liquids in chemistry. We look at indexes of refraction because benzene and all of those are going to be slightly different. Hang on, where's my zoom? And so we have those in there. So there's Snell's law. And it gives us our angle of incidence. Don't overcomplicate it. Just keep track of which one's which. And then we get the idea of dispersion. The dependence on the wavelength on that gives us our dispersion, and depends on the wavelength of light. And then you can see those dispersions in there. Crown glass is going to give you a little bit of difference there. And then we can get our refraction through a prism, which is going to give us that angle of deviation, which will allow us to spread the light. So that's why you can actually start to see the prism effect, was because you are going to see how the different colors will travel through the different distances based on Snell's law. And you can do prism spectrophotometers, and you can identify our gas spectra, which we've already seen. You can get your rainbows, because that's what the water droplet is acting like a prism. It's going to give us our rainbows, and that's what we're going to get those. We can get multi variants in our rainbows, or multi orders that you can start to see that are pretty cool. Huygens principle says that any light on the wavefront will allow a new wave, which is going to allow us to do our slits, allow us to do our double refractions and things like that. And you can use Huygens principle to validate Snell's law, which is nice. And then we were talking about total internal reflection. This is the one where you finally get an angle where the ray cannot bend out, and we get our critical angle, and then everything bends in. And this was what allows us to do fiber optics. So your critical angle is going to look like that, depending on your material. And then you will be able to get your fiber optic cables. You can do a leaky line. You can actually do a fiber optic with, you can take a glass jar and some aluminum foil, create a hole. And if you get your glass jars creating aluminum foil, you can take a flashlight at one end of your glass jar. And if you have a hole cut into the lid of it and you get a nice pour of the water that goes in, you can pour light out of a bottle, which is pretty cool because you can use this idea of your critical angle. And that's what's going to give you your fiber optic, because it becomes a pipeline. And so the fiber optic is what we're doing, is we're using the optical through the glass, and we're using total internal reflection to keep everything inside of our fiber. And that's what allows us to transmit data through the fibers. And that gets us reflection and refraction, and we'll start mirrors on Wednesday. Questions? Yeah. It's the fiber